welcome you to the course on neural science for engineers. This is Srinivas Bhaskara, TA of this course, and we are looking at brain stimulation. In the last lecture, we have seen different aspects of brain stimulation, and we have already covered extensively what is brain stimulation, how brain stimulation works and all right. So, we have seen this what is brain stimulation, why brain stimulation, and how generally we have seen in terms of circuit point of view how the deep brain stimulation takes place, and we already know that why deep brain, because you are in the deeper structures of the brain. So, that is why it is called deep brain stimulation. We have seen these criterias last time, but let us continue with the electrical properties. Okay. So, as you see here, there is something called reverse charge injection capacity and lower impedance. Okay. So, these two things are coming from electrochemical characterization techniques, right. So, what does it mean? It has a lot to do, okay, when it comes to reversible charge injection. Means you are injecting something, means for a stimulating electrode this is most important, and lower impedance, this is very much important for recording electrode. When you are recording signals like ECOG signals or what local field potentials and all, recording type of electrodes, this lower impedance is very much important, very much important characteristic to consider, right. So, what are these? Just briefly I will explain, because I do not want to get into the complex stuff of how the reactions takes place and all those things. So, let us see what we are trying to do is, there is a brain, correct, there is a brain, and across the brain there are fluids. Okay, there are fluids and all those things are involved. On top of this I am putting an electrode, okay, this is an electrode, okay, and there is a electrode tissue interface, correct. So, what happens is, whatever the electrons or charges that are travelling when you are stimulating within the electrode, that has to be converted to the ionic charges across the electrode tissue interface. Okay. It is not like one conductor to another conductor, it is going like this. Okay. This is conductor 1 and conductor 2, the flow will be same, it is not like that. Okay. It is really complex chemistry that are involved. Okay. So, it comes under the part of electrochemistry. Okay. So, what we are trying to see, just I am just giving an overview. Now, according to this, what happens is, okay, you cannot inject whatever we want, are getting it. Suppose when I say inject, whenever you apply some potential to this, or generally these electrodes we can excite them using a voltage source, constant voltage sources, and we can also use constant current sources, okay, anything we can use. Okay. So, let me write here clearly, I can use constant voltage to excite the electrode, or I can use constant current, right. Now, we use most preferably constant current, because irrespective of whatever the impedance is offered by the brain tissues and all, your current will not change, right. And you know what happens with the voltage, as impedance changes, the current through that will change, are you getting it. So, if the current changes, then the charge will change and all. So, most preferable thing is constant current sources are used. Okay. So, can I use whatever the current that I want? No, correct. So, what happens is, generally at the brain interface, whenever you excite this by using some current and all, inevitably you are throwing some charges, okay, you are throwing some charge onto the interface. Okay. When I say throwing means whenever you apply, whenever you excite this with current source, okay, there will be a charge distribution that takes place here. Okay. Right here, if you are familiar with electrochemistry, okay, then how this charge gets converted and then transferred to this medium depends on two things. Okay. So, you have capacitive reaction that is taking place at the interface, or you have Faradaic reaction that is taking place, or both, anything could have happened. Okay. You can have a capacitive reaction, a Faradaic reaction, or both will be taking place at the interface. Now, that will decide, okay, how much current can go inside, and then and how far, how you can retrieve it back. When I say how you can retrieve it back is this. So, whenever you excite something, whenever you excite the membranes, right, brain membranes, right, when I say excite means you are inevitably charge you are transferring, correct, okay, through something like through capacitive means or Faradaic means or both, right. So, what you are doing is you are giving this kind of current pulse. Okay. So, this is a biphasic pulse, this is anodal pulse, this is a cathodal pulse. Okay. So, sorry, this is another way. Let me erase some stuff. Let me get the marker. Okay. So, this is a cathodal pulse, this is anodal, on the x axis it is going to be time, on y axis it could be current, for example. Okay. Now, let us say this is one cycle, right. Let us say this is minus 100 microamperes, you are generating 100 microamperes, correct, plus 100 microamperes, right. Now, we know that charge is integral of q equal to integral I dt, correct. So, when during the cathodal pulse you are transferring some certain charge, okay, let us say this is minus q, right. During the anodal pulse we need to retrieve that charge, so that during one cycle I have net charge q plus q minus q, that is equal to 0. Why means, suppose if there are any charges that are left over on the brain, correct, then some kind of reduction oxidation reactions may takes place, reduction or oxidation reactions takes place, and that will impact the brain, that will impact the that may damage the brain, that may damage the electrode. Okay. So, many things will take place. So, the ideal, this is the most preferred way of transferring the charge, most preferred way, right. So, that is how so now what happens is, when you are doing this, let us say electrical properties we are discussing, right. Let us say some of the metals that we use are platinum, gold, these are also called as noble metals and all those things. Then we can also use conductive polymers like P dot, PSS, okay. Then you can also use alloys, platinum iridium alloys, and so many other things are possible, right. Every material has something called as reversible charge injection capacity. To be precise, this is maximum reversible charge injection capacity, correct. That means, I mean, in a normal terms, I do not want to go into the details about everything about the maximum charge injection, but I will just want to give you some example, right. So, what it is first, what is idea? You have to pump the charge and you have to retrieve the charge, correct, that is idea, correct, no. So, finally, after end of one pulse you have to make sure that the total net charge that is transferred is 0, correct. So, now in this process, okay, there are some material, let us say for example platinum, if you take platinum has a range, okay. So, 50 to 150 microcoulomb per centimeter square, okay. So, this is the charge injection capacity, correct, means if you are sending at the rate of plus 50, you can receive at the rate of minus 50. okay, for a particular material. Okay, it varies. Why sir? This is 50 to 150. It's depends on lot of parameters, because I told you, that's why it is a so much complex thing. I don't want to get into the details of all this, because I have to explain everything from there. Okay, it comes, if you are interested, you can see some articles on electrochemistry about cyclic voltammetry and all. You can understand that. Okay, means for a platinum, let us say for example, for a given platinum material, it has plus 50, or it is not plus, you can just use microcoulomb per centimeter square. This is the charge injection capacity, correct. So, if you use 50 microcoulomb per centimeter square capacity, you can retrieve also at the rate of 50 microcoulomb per capacity. Suppose if you have induced more charge during this time, correct. So, let me take some number and then explain you. Okay. So, let us say for a given platinum, you have charge injection capacity per centimeter square, right. Let us say you take this waveform, right, you have induced the charge, okay, you have injected here, okay. So, 50 microcoulomb per centimeter square, right, and you have a time here, right. So, for this 50, right, you multiply this 50 microcoulomb per centimeter square with respect to the area, okay, you will get the total charge that you can transfer in a particular cycle. Okay. In this cycle, this is the maximum charge that you can transfer. Okay. Now, you got the total charge is, let us say R, this I can call it as CIC, charge injection capacity into the area. Okay. Now, you got the total charge. So, what is Q? Integral I dt. Now, anyways I is a constant, Q is equal to I into, okay, T. Okay. This is nothing but a T cathodal pulse, no, TC, I can call it a TC, this is TA, right, this is IC, okay, this is the maximum amplitude, right. Now, you can calculate what is the maximum current, what is the current that you can, what is the maximum current that you can pump, right. Similarly, you have IA here, right, IA, okay, and what is QA? IA into TA. What is this QC? Charge induced during the cathodal pulse is IC into TC. So, ideally we need IC into TC is equal to IA into TA. Okay, this is the charge balance equation, right. So, what is the maximum current that you can supply depends on the Q, this Q depends on the CIC. Now, you understand the relation. Your maximum current, let me take red pen and highlight the flow. Okay. You don't need to remember or by heart all this. This is very simple mathematics I am doing. Okay. Your Q, your maximum IC is decided by Q, okay, and Q is decided by the CIC, because if you take two materials, let us say platinum or gold with the same surface area, okay, same surface area, what is decided is CIC. CIC will decide what is the Q and Q will decide what is the I. Okay. So, that is the reason your platinum has the range of 50 to 150 microcoulomb per centimeter square, this is the CIC, and for a gold it is around 22.5 microcoulomb per centimeter. There are different numbers. Okay. I am just giving roughly, these are the numbers. Means if I use AU, I can apply lesser current when I compare it with the platinum, because same surface area, right, area is same, assuming that area is same, what varies is CIC. This CIC properties you can deduct from something called as cyclic voltammetry curves. Okay. There is something called as cyclic voltammetry, using which you can deduct CIC. Okay. They are also called CV character. There are so many other things also, right, which is one of the important. Now, you understand the importance, right, of CIC. Means if you want to apply larger currents, you have to go for materials which has larger CIC. Okay. This results to larger currents, right. So, understand this, this is the implicacies of this, right, of this one. Then lower impedance, what is this is, you already know, you give impedance when you are talking about sinusoidal signals, you give sinusoidal voltage multiplied divided by the current that is produced between the electrodes, then you will get something called as impedance. Okay. Now, this impedance can be plotted with respect to frequency, and how does that curve generally looks like? Something as drawn here. Okay. So, the one of the characteristics is, okay, in the research field we look at the impedance at 1 kilohertz. What is the impedance offered by the electrode at 1 kilohertz? Okay. This we call it as a characteristic impedance or generally impedance, right. Now, any guesses whether the impedance is more or less? Okay. So, here for the electrodes with lower impedances, it is observed that, okay, your S and R, signal to noise ratio, is high. So, this is one of the requirement, okay. And this is I already discussed, this is for a recording type of electrodes, very one of the important thing, recording type of electrodes. And not only that, there is something called as chronopotentiometry, which I have not discussed because that is not that is beyond the scope right now, but you can also go through that electrochemistry articles on chronopotentiometry, which from there you can decide on what is the maximum current that you can apply, okay. So, such that it should not fall beyond the safety limits of the particular electrolyte interface, right. So, there are so many other things are involved in that actually, right. So, that is how I am just concluding it, because if I go and discuss about this we can discuss a whole day on that, right. So, these are the, that is why I am telling these are the different criterias for choosing a electrodes and substrate materials, and whenever you are talking about electrode properties and all, you need to go for electrochemical methods and electrochemistry background. People may understand this more, and if at all you are in the neural field research, you need to know more about this electrochemistry as well. Electronics is not alone sufficient, right. So, next thing is I wanted to show you some of the devices that have been developed for rat models. Oh, then people may ask, oh, we are discussing about human brain, suddenly what is this rat thing coming up, okay. So, generally the research goes like this, okay. In the research, right, suppose let us go back to the brain, okay. So, let us say that I am working on Parkinson, and this is found to be the effective target, right. So, how should I prove it? If I at all I have to prove it, I cannot work on humans directly. So, what I should do is first work on the rats, then go for something called non-human primates, NHPs, then you go to humans, like NHPs means the monkeys and other things, okay. So, this is the cycle of a research, okay. That is why lot of research is going in the rats, and then to try to say that see the research is like this, okay. Now, for a Parkinson disease, I said that subthalamic nucleus could be the reason for it, but it is also observed that there are side effects that are associated while stimulating the subthalamic nucleus region, okay. There are side effects that are there. So, now people are moving towards some other targets in the brain, maybe if not subthalamic nucleus, what else could have been the reason. That all those things has to be initially studied in the rat models, okay. So, most of the micro fabrication techniques and all, they use it to fabricate miniaturized devices, so that they can implant in the rat's brain. Now, you can understand, okay, our human brain how much big, and you would have seen the rat how small the entire body is, and you can see the brain, okay, hardly 1 to 2 centimeters, okay, the length of the brain is. In that you have to identify that particular region, and you have to stimulate that particular region, and you have to devise the electrodes, all those things in that particular range, okay. So, generally in the order of micrometer range or nanometer range. That is how that is where the micro fabrication techniques come into picture, okay. So, look at the slide now. So, what we are doing here, if you look at these electrode dimensions and all, See all are in the range of micrometer somewhere, okay. You see this range, the scale is, okay. The entire device if you see just 11.5 mm, right, very very small. And this is the substrate here they used is silicon, okay. So you can see the references I have given in the slide, and then if you are more interested you can go in detail about what are the materials that they have used, okay. So I remember this is a gold that they have used, okay, and this is a the speciality of this device is it has electrodes on the both the sides. Now you see this here, okay. Now let me erase this. So there is this is electrode, there is an electrode, and here it is a contact pad, and these are interconnects, the red color things, right, okay. These are interconnects, which are connecting the electrode to the contact pad, and here the electronics will sit, okay. So you can now this you take it to the electronics part or electronics board, okay. There are some kind of connectors that are available, for example FPC connectors and all, then you just clip in that FPC connector to this, and that is how, and that connector will go to a PCB and all those things, okay. So let us not discuss about more about, I will just show you some pictures in the following lectures, right. So this is how generally anything is fabricated, then how it has to be done, how this structure has been created using something called as fabrication techniques, okay. That is what we are mostly interested in, okay. Fabrication techniques, precisely micro or nano, okay. These are the ranges, okay. It could be micrometer range or it could be nanometer range, right. And this is one example, this is one example of a rigid substrate, okay. Rigid substrate means the substrate that they have used is a silicon, and okay, this is a silicon substrate, right. Now here if you see, okay, this is something different, okay. They use the substrate as a polyimide, okay. I already discussed, this is a polyimide and this is very much flexible, okay. So you can just fold it just like that, right. So if there is a flexible material, how we are going to create these kind of structures over that. See the flexible material is little tricky, okay. First of all, the flexible substrate is the material that is used for a flexible substrate come as a liquid. So that has to be solidified, okay, or cured, right. You spin coat that particular material, and for one of the example for a polyimide I am saying, okay. So for a polyimide, how to get a polyimide, it is like it will come as a polyamic acid, okay. So that is a liquid that has to be cured, okay. So where you will cure it, you will take a silicon wafer, okay. On the silicon wafer you drop cast the polyimide, okay, liquid you drop cast, and then you spin coat it, and once you spin coat it, you do something called as curing, okay. You do 80 degrees curing or 250 degrees or 360 degrees, whatever the process requires or whatever the temperature mandatorily cured, okay. So that particular thing you can take, on that now you have a silicon, on top of it there is a polyimide, right. There is a polyimide material which is all over. Now that you have to take for whatever the next steps are, okay. So like if you want to go for if you want to deposit metals like titanium or whatever it is, you can use PVD technique, CVD techniques, maybe CVD you cannot use for metals and all. I am saying for example, you can use any technique and deposit whatever the material that you want, then you go for create patterns, okay. That we are going to see the example next, right. So this is how you can do microfabrication techniques by using that, right. At the end what we will do, you peel off that polyimide this thing, I mean once you take out the devices, you need to peel it off. Now that device is slow flexible, okay. So it is like this curving, it is not like solid like a silicon, it is like curve, okay. So, now this it cannot be inserted in the brain, okay, because it is so flexible that there is some buckling effect. Buckling effect is something like this, you can see this, right, like this, okay. You cannot insert it properly. This is the challenge with the flexible materials. The advantage is you have mechanical properties that are matching to the brain. The disadvantage is there is something called as buckling effect, right. So, to overcome this, what generally people use is you use a mechanical shuttle around it, okay. So, you put a hard substance along with that, okay, and try to insert it. Once the insertion is done, you take out that shuttle. Are you getting it? Or some other form of shuttle like biodegradable materials you can use, okay, because anyways biodegradable means after some time it is going to be degrade over a period of time. Are you getting it? So, that whatever the material that you like a polyamide along with biodegradable material, for example, PLGA, okay, polylactico glycolic acid, okay, that acid you can use, that is a biodegradable material, but that is little stiff, okay. You can insert it properly, after a week time or 2 weeks time that is going to dissolve within the body without any, I mean not without any, with minimal or with least side effects and all those things. And whatever polyamide that substrate that you have inserted, right, it will be there, and it is the contacts whatever are there or electrode contacts that will be in touch with the brain, okay. So, in any way you can do, that is a tricky with the, that is a tricky challenge with the flexible materials, okay. So, now if you look at the slide, so there is something called as there are electrodes here, you can see the electrodes here, okay. These they used platinum and iridium oxide electrodes, okay, and similar the same structure, okay. You have a contact pad and this goes to the electronic circuit board and all those things. So, the story remains the same, okay. So, if I want to conclude it, okay, so this is how the story goes, okay. So, for every material that you are choosing, it has to satisfy different criterias. We have seen foreign body response criteria, right. Then we have seen biocompatibility criteria, right. Then we have seen it should not generate byproducts, means your material should not react with the electrolyte or with the neighboring tissues and all those things, correct, no, that is also not acceptable. Then second thing is mechanical property, whether it is soft or hard, then other one is electrical properties. And we have also seen what is the challenge with the flexible materials, because they are so flexible you cannot insert it properly, okay. There is something called as buckling effect that is involved, okay. So, these are all the challenges that exist with the flexible. So, what is the challenge with the hard materials like silicon? I told you already, there is something a local irritation that triggers immune response, again local trigger immune response, and there will be different other things are also there, are you getting me? So, you have advantages and disadvantages of the both, and based on that you have to play around, okay. So, in the next part we will see the electronic systems and other aspects of brain stimulation. Thank you.